So, hello and welcome to Wordgrind, a logic programming language for creating quality-based narrative. Today I'm going to do a little interactive presentation about my interactive system and showcase a little demo of its features. But first, let's explain sort of two concepts that are in the title of the talk, which is logic programming and quality-based narrative. So, logic programming is a programming paradigm based on kind of declarative way of writing code. Now, those who have watched John Ingott's talk, where he kind of explained what does declarative programming mean, kind of have a better idea of what is meant by this. But generally, the idea is instead of telling a computer what to do, you instead describe a certain problem. And in case of logic programming, you do it using this mathematical formalism called first-order logic. And then the computer executes the code by solving a certain query that you provided. And this is in some way equivalent to an execution of a program, except that you don't actually write any code per se. You just describe the problem in a way that's more akin to how a human would think about this problem. I know this sounds probably kind of complicated for an interactive fiction tool, but I assure you it's very straightforward once you actually get into it. I will be demonstrating, I'll be doing a live coding demo, so kind of show how it works. And the second concept that I wanted to explain was the quality-based narrative, which is also known as a story-based narrative, which is essentially a work of interactive fiction or otherwise narrative of actually that's a good way of putting interactive fiction, where content is divided into discrete pieces which have certain precondition and certain effects. And these pieces can occur in any order, provided that their preconditions are met. It was popularized by the failed Better Games studio, who worked on Fall in London and a few other games in that universe. I'm just giving a very abridged version because I want to jump in and showcase how to build a simple interactive model using my tool. Now note that this is a very early version of the tool. It is not yet publicly available, and both the syntax and everything else in it may and will be subject to change. So in order to demonstrate it, we're going to build a small game in a live coding session. And the game will be in some sense similar to the old parser-based interactive fiction, where you have several rooms and items, and you can move between them and pick up and drop items. A bit similar to the tool Robin was showing earlier, GruScript. It will be something like that. It won't be parser-based the way all text adventure games are. It will be just similar in terms of the world model that it's going to have. As I go along, I'll be explaining what the primitives of the language are and how it works. So, any questions for now? All right, I'll be moving forward. Let's go. So first, we are going to, because our demo is going to be essentially just a few rooms, a way for the player to walk between those rooms, and a few items inside those rooms the player can pick up and drop anywhere they want. So first, we're going to define some rooms that the player will be moving between. Now, since the fact that something is or isn't a room, it does not really change throughout the game, we are going to do so in a section called the predicate section, which contains all of the facts about the world of the game that remain constant. I may not have mentioned it before, but I am showcasing using an example that's based on parser-based fiction or these kind of text adventures that, for instance, were what inspired GruScript, which was showcased earlier. But my tool is very general and can be essentially used to create, I mean, I don't want to say every possible choice-based game, but the scope of things you can do with it is very big. And one of the reasons why I want to demonstrate using a classic example is because I want to show how easy it is to essentially build something like this from first principles in a way. So we're going to define a few rooms. First, let's define a kitchen. Kitchen is a room. I'll explain a little bit later why we're putting the kitchen part inside of the angle brackets. Then we're gonna have a living room. Then we're going to have a bathroom. And then we're going to have a bedroom. All right. Now that we have the 4 rooms that are going to be in the game, we're going to have to establish which rooms lead to which other rooms, which rooms are connected to one another. So we can write that the kitchen is connected to the living room. The living room is connected to the bathroom, and that the living room is also connected to the bedroom. All right. Now, the thing is, my tool essentially doesn't really know anything about rooms or walking between them or anything else that you might imagine would like a system designed for this kind of game would have. So what I'm doing here essentially, all I'm specifying is that there is some predicate called essentially X is a room, and that there is some predicate called X is connected to Y essentially. So the thing is, the computer at this stage doesn't even know that just because something is connected to some other thing, this means you can walk between those two areas in one direction and the other. So this is what I am going to specify right now. I'm going to declare like an additional predicate called A and B can be walked between. Note that I have this variable syntax here. So essentially, putting a quotation mark between a word means that this word is a variable. It will be substituted for something else. So, but let me first write what this predicate actually does. So, essentially, what it says here is that A and B can be walked between. Actually, I should probably finish writing it before I explain it. So, because otherwise it would make sense. A is connected to B, or B is connected to A. And that's a cosine instead of a dash. All right, so what this essentially means is that A and B can be walked between if either A is connected to B or B is connected to A. So essentially, kitchen and living room can be walked between if either kitchen is connected to the living room or the living room is connected to the kitchen. And in our case, the kitchen is connected to the living room. So it's going to find the first close here, and it's going to say, okay, yeah, that makes sense. A and B can be walked, kitchen and living room can be walked between. So this is fine. Yeah, and these are all the predicates that are going to be in our game. So these are all the immutable facts that our interactive system is going to have. So now we're going to declare all of the things that can change. Let me look at my notes. Okay, so we are going to declare all of the conditions that are the initial conditions that will be true at the beginning of the game. This is the dynamic database. This is all the things that can change during the game. Spelling is hard. Initial, okay? Initial state. And the conditions will be that the player is in the bedroom. The soup is in the... Oh, soap. Sorry, my writing is really bad. I was wondering, why did I write that a soup is in the bathroom? Kitchen would make more sense. right, the TV remote is living room, and knife is in kitchen. And optionally, I can display some text that will be already available at the beginning of the game. So something like, as the player starts in the bedroom, all right, you wake up in the morning, for example. All right. So now, now it's time to specify all of the things that the player can actually do in the game, the verbs, or the choices as we call them in the system. Give me a second. Oh, sorry. Right. So don't worry about the default parts. It's essentially within my system. You can all of the choices that the player will have access to, all of the things it can do. Um, I have a system where these choices are essentially divided into various decks, so that you can specify that, for instance, when a player is in when a specific deck is active, you have a certain limited range of choices. But I won't really be showcasing this feature today because essentially I'm currently reworking it. So anything that I would show you in this current build of the tool, it would not really carry on to any version of the tool that I will be showcasing in the future. So for now, all we need to know is that there is one deck named default, and this is where all of our choices will be living. So the first we're going to start with the ability for the player to walk between one room and the other. So I'm going to create a choice named walk from A to B. And we're going to specify that this choice is available when the player is in A. So what this means that this choice will only be available if there is a clause in the dynamic database called player is in something. And in our case, for our initial state, there is a something. There's a clause called player is. I guess I should use the term structured term. There's a term called player is in bedroom. So essentially, we're guaranteed that when you start this game, there will be an A here, and the A will be bedroom. I heard there are some questions. Okay, not for me. So, player is in A. Okay, available when essentially this expression is used to match terms that are inside of the dynamic database. So everything that can change during the game. But we also may want to make use sometimes of the predicates that are in the system. So for this we use such that. Basically the same, only this one is for the dynamic database and this one is for the static predicates we have declared. And we're going to say that this is available when, when players in A such that A is a room, B is also a room, and A and B can be walked between. All right, and this causes that the player is in B, location B, and we can add a little message here that it's this place you walk from A to B. All right. Yeah. So essentially, the way this works is that A is already matched to the room that the player is in, thanks to the available when portion here. Now B can match to absolutely anything that is a room. So anything that we have declared in the predicate section as a room. And A and B can be walked between. So this can match to anything that we have specified is connected together. So actually, let's run this and see if it works. Um, hmm. Okay. One second. Okay. Hmm. Great. Let me do this the another way. Having a small technical issue. Alright. This really doesn't look right. Well, I can continue. I can continue with writing the model for our game, and then at the end, I'll see if I have time to fix my technical issue with actually compiling it and showcasing how it runs. In the meantime, I'll answer some questions. Do you have time to do you have to delete the players in AFACT? Ah, that's actually a very good question, and I wanted to address it near the end. The way I'm solving this issue is slightly different than Scepter does, because in Scepter you essentially have to specify that a certain thing remain constant, because otherwise it's assumed that it will remove all previous versions of that term. Whereas here we do it the other way around. Actually, I'll showcase when I get into it, but for now I'll just continue with showcasing the different choices we have. So, right, we have implemented the ability to walk between one room and another. You have to believe me on that one. I will show it later, hopefully. So next, we're gonna have to add the ability for the player to pick up an item. All right, so the option to pick up an item is available when a player is in a certain place. How are we doing with time, by the way? Oh my god. Yes, I only have 5 minutes. Actually, since I'm gonna implement the pickup function, and since I don't really have the time to showcase I mean, due to technical limitations, I probably won't be able to actually showcase it running. I'll take questions after I'm done with it. All right. Player is in a certain place, and an item is in that same place. So, and this causes the player to have an item, and it removes the fact that the item is in a certain place from the database. So essentially, you have to specify that something is no longer true after it has matched into it. Yeah, and the reason why I didn't do this in the walk from A to B predicate is because we have the ability to specify certain things as unique facts. And in our case, we specify I believe player is in to be a unique fact, which means that every time you add player is in X to the database, it automatically replaces the previous value. Okay. Well, I wouldn't really call this exclusion logic. This is like what I'm doing here is babies first, exclusion logic maybe. But I've been thinking about implementing exclusion logic in this tool. Uh, yeah. Friendlier version of exclusion logic. Because I read the Versa paper and I thought it was a really cool solution what they had here, and maybe it would make sense to implement something like this in my tool. But if there are issues with user friendliness, I don't know. I'll think about it. So, are there any questions? I'll quickly see, and maybe I have some old version of the tool that's. Uh, are there any questions at this point? Mm-hmm. Does it think is a? No, it is considering it to be a unary predicate. Essentially, the way this works is that those the items that are in the brackets, these are like essentially what we would call atoms in Prolog. So this the brackets indicate that this is the place where like you can put a variable or another structured term or an atom. Player isn't really any special than anything else. It's just and it's just like the only reason why it's special is because I specify players and predicate as a unique fact here. No. All right. It's not. No, essentially, right. At least right now, and I probably wouldn't want it in the future. We don't really have any special kind of words that are treated differently that don't need brackets. Essentially, you have words that are in brackets, and you have variables that start with the question mark, and everything else is treated always the same.